One and welcome in this video where we will solve some exercises about commutators. Commutators, which is a physical or mathematical concept that we has introduced in the previous video, where we introduced the concept of operators. If you didn't look, I advise you to watch this and put like in this video, share with your friends, subscribe in our channel. Then in this video we will solve some exercises about commutators, where the first one we want to show these two identities, where we have a commutators of operator A with a product of operator B and C, and we want to show that this commutator can be rewritten as this sum of two of these commutators multiplying with this operator, with the C operator, and B multiplying with these commutators of A and C. Okay, we have the other exercise with this one to show this expression, and we want, for example, here we can see for the second exercise we will try to solve these three exercises, where these we can put here this has B and here this has C. Okay, where as we can see here is we can apply directly the same procedures that we will apply. We can use these two identities to solve these exercises. Okay, here P is the momentum operators, and we define the momentum operator as with this expression. The third exercise is to verify. We want to verify the Jacob identity, which is this where we can see here we have commutator of operator A with the commutator of B and C operators, plus the commutators of B with the commutator of C and A operator, plus the commutator of C and the commutator of A and B, and we must show that actually this is equal to 0. And as the last exercise, we will also solving these commutators of, as we can see here, is the angular momentum with the linear momentum. We have this here we have the component of the x component of the angular momentum commutating with component of the x component of the linear momentum. Here we have the commutator between two different components of angular momentum, where we have x and y components, and we have the definition of angular momentum in its x component has y times pz minus z times py, and we have also here the definition of the y component. Then we will start here solving the first exercise A, where the first exercise is ABC. Okay, A, we want to show that the commutator of operator A and B, C, it's equal to B, A, C plus A, B, C. Okay, then To solve this, we will start with the definition of a commutator. We know that, here, definition, we know that a commutator D, the commutator of D and E operator is actually, is D times E minus E times D. Then we must use the same definition for this case, where we have then A, B, C. Here we consider this has our D operator, and this product has our E operator. Then we get here A times B, C minus B, C times A. And here also we can see that we have these two terms where we have A, we have A without including on the middle term. Then we can add and subtract, for example, B A C minus the same term, which is B A C. And now we can, for example, working with this term with this one, and this term with this one. This with this one, so that we can write now A B C minus B A C plus B A C minus B C A. And we can see for now we have C here, so that we can take its evidence, and we have A times B minus B times A times C. And also we have here, for example, we have here B and B, so that we can take its evidence as B times A times C minus minus C A. And has the definition of a commutator, then we have here the commutator of A and B times C plus B times the commutator of A and C, which is also actually equal to B commutator of A and T plus A B commutator times C. Okay, then we have shown now that actually we have this identity has equal to this one, as we have here this equal to plus this, which is equal to this identity. Here we must remember that here this only we are sum with 0, because we have B times A times C minus B times A times C. Then we have here 0. Okay, we go on with the next exercise, which is B. Okay, ABC, and here we have showed that A B C is equal to B A C plus A B, C. Okay, we go on with the second exercise, which is commutator of the product of A and B and C to show that this is equal to A times B C plus A, the commutator of A and C times B. Also, we will use the same procedure as the previous exercise, and we have A B C is equal to A B C minus C A B. Again, we can see that here we don't have C on the middle term. Then we can sum here a term, for example, A C B, and subtract the same term, which is A C B. And from here we work this term, for example, with this one, and this with this, and we have A B C minus A C B plus A C B minus C A B. And now we have we take A as we take the evidence of A, and we have B C minus C B plus, here we have B and we have A C minus C A times B. It's necessary to remember that generally the product of two operators is not commutative, so that is very important to verify that if you have the operator on the left hand side, then you must guarantee that you have also the same operator on the left hand side, and you have the other operator on the right hand side. You must guarantee that it's present on the right hand side, as we can see here. Okay, and from now we have that we have here A, and this is commutator of B and C, plus this is the commutator of A C times B. And now we have verified that actually this commutator can be written as A times the commutator of B and C plus the commutator of A and T times B, as we have here. Okay, we go on solving the number 2 exercise. Okay, we have A, B and C. Sorry, here I forgot in square. Yeah, square. Okay, we have now the second exercise with A, the commutator of Z, and the linear momentum, the Z component of the linear momentum. We have B, which is square root, the commutator of square of Z, and B, sorry, and the Z component of the linear momentum, and C is the commutator of square of Z, P of Z square. Okay, where here we have the component, the Z component of the linear momentum written as minus I H bar D of X. Okay, Then to get the solution for this, we have for A we have z p, and as we showed in the previous videos, we must put here any function f, c, or any function that you need to get the correct answer, where you have here, for example, z time p z minus p z z acting all these acting on the function psi, and now this is actually z p z minus, oh sorry, here acting on psi function minus p z acting on z time psi. Here we have that by definition of the z component of the linear momentum, then we will substitute this. We have minus h, it's a constant, then we can get out from all other elements in our exercise, and we have here z time d of psi over d of z minus now we have the derivative d over d of x of z psi, and here we have that, sorry, and here we have minus I h bar time z time d of psi over d of z minus here we have firstly d of z over d of z time psi plus z time d of psi over d of z, and now we have minus I h bar time z d of psi over d of z minus psi, sorry, here, okay, this is 1 because we have d of z over d of z, and we have 1 time psi, which is psi, minus z d of psi over d of z. As we can see here, this term is equal, sorry, this term is equal to this one, so that we can simplify, and we have only minus psi here, and we have the solution written as minus, oh sorry, this minus time this minus is plus, and we have only I time h bar psi, and this means that z, the commutator of z and z component of p, it's equal to I time h bar. Okay, maybe here I can tell you about the concept of commutator. When can we say, when we have talked in the previous video, what's the consequence of the commutative, what's the consequence of two operators commutate between them? If two commutators will commutate between them, we know that their commutator is equal to 0. Yeah, this means that we can actually observe simultaneously in an experiment the eigenvalues of both operators in quantum mechanics. But if two operators don't commutate between them, then we can only observe one time each one. For example, we know from the uncertain principle, or the Heisenberg principle, that we don't we don't have how to measure we don't have how to measure at the same time the position and the momentum of a particle in quantum mechanics. This means that the operator of position and the operator of the momentum doesn't commute between them, as we can see here. If the position, for example, we are measuring in z direction, and we also try to observe the z component of the momentum of this particle, we don't have how to measure, we don't have how to observe the same we don't have how to measure both physics properties at the same time. We can only measure one by one at each time. Okay, we go on with solving the line B, which is z square. Okay, we have B here. We have B here, which is the commutator of B of z square and bz. Then from here is the same thing written as commutator of z times z here, pz, which is, as we saw previously, which is equal to z, the commutator of z and pz, plus z, the commutator between between the commutator between z and pz times z. And now we know that this is actually I times h bar, and here also it is actually I h bar. Then we have as the solution for this exercise I h bar z plus I h bar z, which is equal to 2 times I h bar z. This is the solution, and we go on with for the last exercise for this number, which is z square and pz square. Here also we can say this is equal to pz square, which is actually z here sorry, we have here z pz square plus here, okay, z pz square times z, which is, now for the first term we have z sorry, I can rewrite this as z pz times pz plus z pz times pz times z. And now we have z times pz times z pz here plus z p z times pz plus the second term, which is pz. Here we have z pz plus z pz plus time pz plus times z here. Okay, and we know that this is equal to ih bar. Here we have also ih bar, we have here ih bar, and we have here ih bar, so that we have now z times 2 times ih pz plus here we have also 2 times I pz this time z. And actually, if from here we apply a function psi as we have worked previously, we can see that here we have minus ih bar d over d of z, and here also we have minus ih bar d over d of z, so that we have now I will write this as minus ih bar times ih bar here 2 times h bar, and we have z here, this one we have z here, d of c over d of z plus again here I have 2 times I h bar, which is this term, times minus I h bar, and we have here d over dz times z times c. And here we can see that we'll leave this as, and here we have d of z over d of z times c plus z d of c over d of z. So that we have now has the solution written as minus h times 2 ih bar z d of c over d of z plus 2 I h bar times minus I h bar d, here we have 1, then we have only c, which is this, plus again 2 I h bar minus I h bar times this term, which is z times d of c over d of z. Okay, now we can see here that we have, if we take out the psi function, if we take out now the psi function, this simply means that we must take out in this term, and we can see now when we multiply this by this one, we get the pz component of the linear momentum. And also here, if we multiply this by this term, we take again pz component, and we have this has 2I h bar times z p z plus okay, so yeah, plus, because if we multiply I by minus I, it's equal to 1. Sorry. And we have 2 times h bar square plus again 2 times I bar z p z, and as the solution we get 2 times 2 times h bar square plus 4 I h bar z p z, and this is our solution for this case. Okay, this is the last exercise for the number 2, and we go on solving the number 3. Okay, the number 3, which is to verify the Jacob identity. Okay, number 3, we must verify the Jacob identity, which is A commutators of B C plus B commutator of C A plus C commutator of A B, which is equal to 0. Okay, has the rule of commutators. We have, for the first one, we have A time B commutator of B and T minus commutator of B and T times A plus the second commutator, which is this one, we get B times C commutator between C and A minus C commutator between C and I times B plus the last commutator, which is C commutator times the commutator between A and B minus commutator between A and B times C. And we go on here for this first time we have A times B C minus C B minus for the second term we have BC minus C B times A, plus for this term we have B C times A minus A times C minus for this term we have C A minus A C times B, and for this one we have plus C times A times B minus B times A, and for the last term we have minus A times B minus B times A times C. Okay, and now we have A B C minus A C B minus B C A plus C B A plus B C A minus B A C minus C A B plus A C B plus C A B, I'm here, minus C B A minus, now I'm here, I have A B C plus B A C. Okay, for now we must only compare terms to get 0. For example, I have here this ACB which is minus, and I have here the same term but which is plus. Also I have here CAB which is minus, and I have also here CAB which is plus. I have here ABC, okay, which is plus, and I have also ABC which is minus here. I have BCA which is minus, and I have here BCA which is plus. Then I can simplify. I have here CBA and which is plus, and I have also here CBA which is minus, and I can simplify. And for the last term I have minus BAC and plus BAC, then I simplify, and so here we can see that we get 0. Okay, I think we can continue solve the last exercise, which is the commutator between components of angular momentum and linear momentum. Okay, I will leave this exercise for another video because this is so long. Then thank you for watching this video. Look for the next video where we will continue solving this exercise. Thank you. Put like in this video if you like this, and share with your friends, and again subscribe in our channel. See you on the next video. Bye.